Alright, so hello everyone. Today we are going to study some chemistry. Before you noticed, yeah, this is in Spanish, the practice test that I'm gonna explain. But yeah, this is my channel and I can mix languages however I want. So yeah. Anyway, let's get to it, I guess. Alright, so let's start with the first question. Okay, so the first point is to compare the difference of chemical and physical properties between metals and non-metals. So let's get to it. First, starting with the physical properties, we have appearance, which you might have noticed. Metals are shiny. For example, this water bottle right here is kind of shiny. Meanwhile, non-metals are, let's say, more dull. They don't have that same like metal polish, and I know that's kind of redundant. But anyway, talking about density, well, metals have a higher density than non-metals. For example, carbon and lead, they are in the same group. But carbon is a non-metal and lead is all the way is down, is lower to carbon, and it has more metallic properties, one of which being it is more dense than carbon. Also, metals are ductile, they are malleable, they have a great thermal and electrical conductivity, and they have very high melting points and boiling points. So the opposite can be said for non-metals. They have low boiling points, low melting points, they are not really good at conducting electricity or heat, they are not ductile, they are not really malleable, their density is lower compared to that of the metals, and that would be mostly it for physical properties. Oh yeah, but before we continue with the chemical properties, I'm gonna explain a little bit the difference between ductility and malleability. So if an object is ductile, that means that it can withstand stretching forces. For example, think about copper wires. If copper wasn't ductile, then we wouldn't be able to make wires out of it. About malleability, well, you might have a more intuitive understanding of it. If something is malleable, then you can deform it without breaking it. For example, with this bottle again, I could deform it, I could punch it, I could hammer it, and it wouldn't exactly break, but the bottle would deform, would change shape. Instead, if I have something that is not malleable, then it's something that we can call brittle. For example, glass. Glass is kind of brittle. You can't really deform it much because it breaks easily. All right. So let's continue with the chemical properties. Now, generally, electronegativity goes up in this. Oh, this so in this sense of the periodic table. Sorry, it's kind of counterintuitive because this is my left to right and this is your left to right. Anyway, I'm actually gonna put an image of the periodic table in here, so give me a second. All right, here it is. Oh wait, I actually think I have one in here. There it is. It's kind of big. Oh my god, this is so laggy. All right, let me. Yeah, you know what? I think I'm just gonna use the this. This is quicker, honestly. Anyway, so I was talking about chemical properties, and now we can talk about periodic properties of the periodic table. So, for example, electronegativity. Electronegativity is about bonding. It's about how much an atom attracts electrons when it is part of a bond. Yeah, all right. So, electronegativity rate goes up from here to here. Yeah, let me see if I can make this. Yeah, in this kind of sense. So fluorine is the most electronegative element there is. It has a 3.98 electronegativity in the Pauling or Pauli scale, or maybe even 4. And if you go from the top to the bottom, well, the electronegativity starts to decrease. That's the same if you go from left to right. Well, this is my left and this is my right. If you go from right to left, the electronegativity decreases. And you might ask, why is this? Well, I'm gonna explain it to you in a second, but what it concerns with metals and non-metals is that since the non-metals are in this side of the periodic table, well, they are more electronegative than the metals. This is the reason why when we have a salt, so a metal and a non-metal forming an ionic bond, for example, sodium for example, table salt, sodium chloride. Well, the chlorine ion, the chlorine is the ion, is the anion, has the negative charge when the molecule, let's say, breaks into the sodium and the chlorine. Chlorine has the negative charge because chlorine is more electronegative than sodium, and sodium has the positive charge because first it just has one valence electron. We're gonna get to that later, but also because it is less electronegative than chlorine. All right. So, all right, let's continue with the chemical properties. So, ionization energy. What is this exactly? I'm gonna tell you in a second. All right, so now we go on to ionization energy. This is the energy that's required to take away an electron from an atom or ion in its gaseous state. All right, and this is kind of similar to electronegativity in the sense that it increases this way. So, for example, fluorine is the most electronegative element there is, and it's also one of the elements with the highest ionization energy. This also means that the non-metals have a very high ionization energy compared to the metals. So let's go from the seventh group of the periodic table to the first, the alkaline metals. The alkaline metals, so like lithium, sodium, potassium, so on, have very low ionization energies. What does that mean? That means that if you have one, let's say sodium atom, then you won't need really much energy to make it lose an electron. Why is this? Well, because the alkaline metals have just one valence electron, so it's kinda easy to just take them away, because when they lose that one and only valence electron, they then have the electron configuration of a noble gas. So for example, let's say we take an electron from, again, sodium. Well, it will then have 11 protons and 10 electrons, which means that it will be positively charged and it will become a cation or cation. and it will have the electron configuration of neon. Yeah, this will make the atom more stable, and the sodium atom will be happier because of this. All right, so let's get moving. This is pretty much the most important stuff. Um, so yeah, that is kind of the thing. Also, metals tend to form metallic bonds, um, and non-metals tend to form covalent bonds between them, and polar covalent bonds between themselves and the metals. Of course, this depends on the difference of electronegativity, and we are gonna get to that later. But before that, I want to explain a little bit more about this, about the metallic bonding. This is a very special kind of bonding that non-metals can do, and it basically means that in a metallic bond there is not really bonds exactly like in the covalent bond where just two electrons are shared, but is instead all of the atoms of the metal create, let's see, like a big cloud or big sea of delocalized electrons. So the electrons are free moving in this metaphorical sea. This is one of the reasons of why that explain why metals conduct electricity so good, so easily. Well, because they have this sea of electrons where the electrons can just flow rapidly and without much problem. Of course, some metals conduce electricity better than others, but in general, metals conduce more heat and more electricity easier than non-metals. And well, now we can go to the second question, which is specify the group in which every single one of these elements are encountered. So here they give us the electron configuration of four elements, A, B, C, and D. And we need to say, well, if you have the electron configuration, then what group are they in? All right, so let's get back to our periodic table in, oh, give me a second. I will take this little image right here, and I will put it next to our table. Here. Okay, so let's go with the first element. And it has the electron configuration of a neon, so 1s2, 2s2, 2p6, and then it has a 3s1. What does that mean? Well, that means that it has one electron in its last shell, in its valence shell. So it has one valence electron. Give me a second. Which makes it pretty obvious that this element needs to be in the first group of the periodic table. But you might say, well, some metals in this region have also one valence electron. I don't exactly know which ones. I'm still studying this thing, but anyway. But we can be sure that this is an element from group 1. Why? Because it has the electron configuration of neon and then one extra electron. So neon has 10 electrons. As I was saying, neon has 10 electrons, and then we add one more, that is 11 electrons, and that should correspond to 11 protons. We are assuming here that this electron configuration is of a neutral atom. We are not talking about ions, cations, anions. So we are assuming this is an atom in its neutral state. So if an atom has 11 electrons in its neutral state, it should have 11 protons. And which element is the 11th of the periodic table? Well, it's sodium. And where can we find it? In the first group of the periodic table. So this first element is sodium, and it is in the first group in the alkaline metals. Then we go to the p element. It has 3s2, 3p3 electron configuration after neon. So we know that it has 15 electrons. We know that its valence shell, it has 5 valence electrons, which means that it should belong to the fifth group of the periodic table. Well, 5a or 15 group of the periodic table. So this element should be phosphorus. In this case, we are not being asked to name the element, just to say what is his group. And for B is the group 5 or group 15 of the periodic table. Then for the C element, it has an electron configuration of 3s2, 3p6, and if you notice, it has the electron configuration of neon and then 8 electrons more. It has a full, it has Oh, it has a full valence shell, so his third level is full. It has the 8 electrons. That means that it is a noble gas. So it is on the 8A group or 18 group. And finally, we've got this D element with argon electron configuration and then 4s2, 3d8. This is a tricky one. Well, it was kind of tricky for me because for a second I thought, oh well, it has 8 electrons in its valence shell, so it maybe is a noble gas, or it has 10 in total, so I don't really know where it should go. But then I realized that the 4s2 is it last its ultimate energy level, and there it has 2 electrons, so we do not really need to concern ourselves with this 3d8. The only thing that matters is that it has a 4s2 electron configuration, so it has 2 valence electrons. That means that it necessarily belongs to the group 2 of the periodic table, so it has so it should be here in the group 2. Well, that's what I would have that's what I would have told you, but if I didn't realize that it actually belongs to here, the group of nickel, or the group number 10. And this is kind of weird, but really it belongs to the nickel group. A way to notice it is that it has the electron configuration of argon, so 18 electrons, and then we add another 10. So in total it has 28 electrons. And which element has 28 electrons? Well, nickel, because it has 28 protons. So yeah, that D was kind of tricky, but in the end you can realize that an element with 28 electrons really cannot be in the second group, because if you have memorized the the amount of electrons that each noble gas has, like I'm doing, you have 2 electrons, 10, then 18, then 36. So if we go from 18 to 28, well, then we have already passed the first and second group. So it needs to be in the D block of the periodic table, or maybe even in the P block, but really in this case it's the D block. And yeah, basically that's how you can say that it is not in the second group, but it is in reality in the group number 10. Another explanation for why this D element, this nickel, is in the 10th group is because for the elements on the block D, the D orbital also contributes to the valence electrons. So in this specific case, well, we need to count 2 plus 8 electrons in the valence shell, so it would total 10. All right. Now I think we can go to the next question. All right, so let's go to question number 3. Write the electron configuration, abbreviated, of the following ions. So the ions are Na plus, Na plus, sodium, a sodium cation, a zinc cation, and a chlorine anion. So Na plus has the electron configuration of neon. Why is that? Well, because sodium has 11 electrons normally. If you take one away, as we said earlier, then you will have only 10. That is the electron configuration of neon. Then we have zinc 2 plus. The normal electron configuration for zinc is the argon configuration 4s2 3d10. So zinc has two valence electrons, and we take two of them away. So it is left with the electron configuration of our argon 3d10. We do not take away the two electrons from the 3d orbital. Instead, we take them from the 4s orbital because it's farther away from the nucleus. So it's technically higher than the 3d orbital. And then for chlorine anion, well, chlorine has normally 17 electrons. We add one more. We have 18. That is the configuration of a noble gas, specifically argon. Now, this is pretty straightforward. So now we can move on to the fourth question, which is which one of the next ions has the smallest atomic radius? This is actually a very interesting one. So give me a second, I take some water. All right. So how do we know? Like, this is the answer. Aluminium 3 plus has a smaller atomic radius than Na plus, and it has smaller than O2 minus and smaller than S2 minus. But how do we actually know? Well, we do that by comparing the number of protons to the number of electrons, and this has a very special name. If I don't remember incorrectly, it is an isoelectronic series. So it's a bunch of ions, anions and cations that have the same amount of electrons but different amount of protons. All right, so to answer this question, well, we need to know what is the atomic number or the number of protons, which is the same, for each one of these elements. So Na, sodium, has an atomic number of 11. It has 11 protons. Aluminum has 13 protons. Oxygen has 8. And sulfur has 16. So they all have different amount of protons, right? But they will have the same number of electrons in their they will have the same number of electrons, almost, you will see. So when we have Na plus, we used to have 11 protons and 11 electrons, but we take an electron away, so now we have 11 protons and 10 electrons. All right. Then we have aluminum 3 plus, and that means that we have 13 protons and 13 electrons. We take 3 away, we have 13 protons and 10 electrons. So let's compare these two instead of comparing the four at the same time. Which one between aluminum 3 plus and Na plus will have a smaller atomic radius? Well, how could we know? It's actually kind of simple. The smaller atomic radius will be in the atom that has more protons with the same amount of electrons. So in this case, the smaller atomic radius is in the aluminum cation. Why? Well, because we have the same 10 electrons, but we have more protons in the nucleus. So the protons attract more tightly the electrons. Instead, in the sodium cation, well, we have the same amount of electrons, but less protons. So the electrons are less attracted to the nucleus, and they can range more freely. So the atomic radius of Na plus is greater than Al3 plus. The same logic can be applied for the O2 minus compared to the other two. We can notice easily that the oxygen has less protons but the same amount of electrons, so the electrons will be more free to move around. So the radius of the oxygen 2 minus will be greater than that of the other two. And finally, we have sulfur 2 minus, S2 minus. This has a greater atomic radius. Why? Because sulfur in this case has the greatest amount of electrons. So the electron cloud, the atomic radius, will be bigger. Even though it has 3 more protons than aluminum, it has 8 more electrons. So obviously the electrons outweigh the protons in this exchange, so the atomic radius is bigger. So what is the correct answer? Well, the Al3 plus has the smallest atomic radius. Alright, so we go on to the fifth question. Which of the next sentences is incorrect? The first sentence is that the chlorine anion has a greater radius than chlorine. The second is that O2 minus has a smaller radius than fluorine minus. The third sentence is that beryllium or B2 plus has a smaller radius than beryllium, and the last one is that Na plus has a smaller radius than K plus. Alright, so let's go first into each one of the true sentences and explain why they're true. The first one, so chlorine minus has a greater radius than chlorine. This is true. The reason is that chlorine minus has the same amount of protons but one extra electron. So this extra electron increases the radius of the atom because it's an extra thing that is orbiting around the nucleus and it can't just be in the same place. Well, obviously not exactly the same place, we will get to atomic orbitals later, but let's say it that way. It can't occupy the same space as the rest of the electrons, so the electron cloud of the atom has to expand, has to be made greater to accommodate the extra electron. Of course, this is an oversimplification, but this is enough to answer this question. So the next one, the next true sentence. B2 plus, Be2 plus has a smaller radius than Be. This is true because Be2 plus has the same amount of protons as Be, beryllium, but it has less electrons. So there are less electrons that increase that make up the electron cloud. So the radius is smaller. And now we, in the last true sentence, we are comparing Na plus to K plus. Why is Na plus? Why does Na plus have a smaller atomic radius than K plus? Well, the reason is very simple. Because Na plus is one period, one level. Well, one. Yeah, I think it was called period. One period before K. So it has a full level less than K. So it has less electrons. It has less protons. So the atomic radius is lesser. And finally, the wrong thing. Why is it wrong that O2 minus has a smaller atomic radius than F minus? Well, if you see, oxygen is 6, well, is 8, sorry, has 6 valence electrons, but it is number 8 in the periodic table. And fluorine is number 9 in the periodic table. So the difference in protons is just 1. Okay, so what happens when we have O2 minus? Well, we have 8 protons and 10 electrons, right? And what happens when we have F minus? We have 9 protons and 10 electrons. So we have an atom with the two atoms with the same amount of electrons, but one has less protons, another has more. So which one is going to have the smaller atomic radius? Well, it's going to be the one with the most protons. And since fluorine has more protons than oxygen, then the atomic radius of fluorine minus is going to be less than O2 minus. So O2 minus is going to have a greater atomic radius than F minus. That means that this sentence is wrong. Now we can go to the sixth question. All right, so now we go to a true or false kind of question. First sentence, every noble gas is diatomic. This is completely false. Noble gases are called noble gases because they are not very reactive. They usually, most of the time, well, there are a few exceptions, they don't form bonds. And being diatomic means that there is a bond between two atoms of the same element. So that is contradictory. A noble atom, a noble gas cannot be diatomic. For example, there is diatomic chlorine, diatomic oxygen, diatomic nitrogen, diatomic hydrogen, but there are non-diatomic noble gases. So next one. The ions K+, Cl+, and Ca2+ are isoelectronic. That is true. If you count the electrons of K+, they are they are 18, so 10 plus 8, because K is the element 19. If you take away one electron, you will get 18. If chlorine, it has 17 electrons normally, you add one more, then you get 18. And calcium has 20 electrons normally, you take 2 away, then you get 18. So they are elements with the same amount of electrons but different amount of protons. That makes them isoelectronic. Next, the metallic character increases from left to right in a period. That is not right. The metallic character increases from left, decreases. The metallic character, sorry for the pause, I was thinking. The metallic character decreases from left to right. So for example, let's go to our trusty periodic table here. So this is the left of the periodic table and this is the right. What this sentence is saying is that from here to here, the metallic character increases. But that is not true. It's actually the opposite, because in this side, there are the non-metals, and in this side, we have the metals, the alkaline metals, the uh, alkaline metals. I don't know how to say that in English anyway. So actually is the other way around. The metallic character increases from right to left. So yeah, that's why that sentence is false. Now we go on to the last affirmation, that elements on the same group always have the same physical properties. This is wrong. Why? Well, we can just see any group really. For example, the group number 14 of the carbon group. My favorite group because it has carbon. In this group, we have a non-metal, we have metalloids, and we have metals. So this means that these elements have different physical properties because they ones are metals, ones are metalloids, ones are non-metals, and we have already seen that they have different physical properties between the metals and the non-metals. So although they are on the same group, they do not have similar physical properties. Of course, there are some general similarities, but they do not have the exact same physical properties, and that doesn't always apply. So yeah, let's go to the next question. Which one of these three metals will react more strongly with water? So we have three metals: beryllium, magnesium, and rubidium. The answer is rubidium. It will react more violently, more forcefully with water. Now let's go again to the periodic table to see why. The reason is that rubidium is on the first group of the periodic table, meanwhile beryllium and magnesium are on the second group. So rubidium just has one valence electron, which makes it so that it loses that valence electron more easily and more violently than beryllium and magnesium. Other reason is that rubidium is lower down on the periodic table. So the valence electron is farther away from the nucleus, so the nucleus has less pull on the electron, so the electron will just go away more easily. You can watch a very interesting video of the alkaline metals reacting with water, and each step that you go down the periodic table, the metal goes boom even bigger, basically. So yeah, rubidium will react more violently. Now we go to the question number 8. Give me a second, I will drink some water. Some water or water. Given the following elements: magnesium, phosphorus, chlorine, sodium, and arsenic. I think I think that's how you say it in English. Anyway, if we organize them from less to most ionization energy, what will we have? Okay, so what is ionization energy? Ionization energy is, we have already defined that, is the energy that is required to pull away an electron from an atom in its gaseous form, or an anion or a cation. Well, from an atom or a cation or an ion, sorry. Okay, and we have already seen that the elements that are on this side of the periodic table, so my right, your left, have less ionization energy, because it's easier to, for example, pull away the electron of a sodium atom than the electron of fluorine. So we already know that sodium will be first on the list, so the D list cannot be, because magnesium does not have less smaller ionization energy than magnesium. So which one of these elements has the greatest ionization energy? That would be chlorine. Why? Well, because it's the element that is the most right of all of them. So it will have the greatest ionization energy. Also, it is the one that is tallest. Well, that is almost highest to all of them. So phosphorus is left to chlorine. Well, is left to chlorine, not exactly next to, but on the left side of chlorine. So it has less, a smaller ionization energy. Arsenic is lower down than phosphorus, so it will have less ionization energy, because if you are lower down, the electron is farther away from the nucleus, because there are more levels, electron levels, that separate the valence electron from the nucleus, so the ionization energy will be smaller. And magnesium is all the way on the left side of the periodic table, so it has a smaller ionization energy than arsenic, phosphorus, or chlorine. Now we go on to the 9th question. Alright, so now we're getting into electronegativity. Tell which one of the following sentences is correct, basing on the electronegativity of the given elements, in terms of the kind of bond that the following elements will form. So the first sentence is hydrogen and hydrogen will form a covalent polar covalent bond. That is not true, because they are the same element, so their electronegativity is the same. So they are not going to form a polar bond, because for them to form a polar bond, the electronegativity between two elements needs to have a difference of at least 5, maybe 7. I think it was 5. Anyway, so next sentence. Hydrogen and chlorine will form an ionic bond. Is this true? Well, no. Hydrogen and chlorine do actually have different, very different electronegativities, but they are not different enough so as to form an ionic bond. Also, hydrogen is not technically a metal, so it will not form an ionic bond with a non-metal. That is another way to justify it with that general concept. Then the D, which is also false. Hydrogen and bromine form a covalent and um, non-polar bond. This is not true. Hydrogen and bromine have different enough electronegativities as to form a polar bond. Alright? And then we have the C, which is the correct one. Potassium and fluorine form an ionic bond. This is true because potassium has a very low electronegativity, meanwhile fluorine has the highest. Another reason to justify this is that fluorine is a metal, is a non-metal, sorry. Potassium is a metal, so a non-metal and a metal will form an ionic bond generally. And now we can go to the 10th question. Represent the Lewis dot structure of the following species. Oh boy. Alright, so we're gonna start with CH3, CH3 plus and CH3 minus. So normal CH3, well, we have a carbon and then we have a hydrogen and a hydrogen and another hydrogen. And we first draw the simple bonds. But the thing is that carbon has 4 valence electrons. So there is an extra electron here. We have 1 electron, 2 electrons, 3 electrons from carbon, and there is the fourth here. So give me a second. So theoretically, well, in principle, this could be the Lewis dot structure for CH3. But this is kind of weird because there is no electron pair in here. So I'm going to leave it up to you. But talking about CH3 plus, it's actually pretty easy. We just have this. We have the carbon with simple bonds to every hydrogen, and that would be it. If we talk about CH3 minus, well, then we have this, a lone pair in the carbon, and pretty much that would be it. Alright, so now we go with NO plus. Alright, so we obviously need to start with the nitrogen, and then we have an oxygen, and we have a simple bond. So here we could do some math, some arithmetic. We sum up the valence electrons of nitrogen and oxygen. So we have 5 plus 6 minus 1 because there is one electron left, one electron less in the molecule, so as to make it a cation. And that is equal to 10. So in total, we need to have 10 electrons in this Lewis dot structure. We already have 2. We need to complete the octet for every single one of these elements. So to make that for oxygen, we would, for example, make a double bond and then add here 2 lone pairs. And then with nitrogen, we would just put here 2 electrons. And then we would have 2, 4, 6, 8, 10 electrons in total, and there would be a positive charge in here. But there is a problem. If we check the former charges for nitrogen, it would have a former charge of +1, and oxygen would have a former charge of 0. But that does not mean that this is the best way to make things. Alright, so Of course, the formal charge on this nitrogen would be +1, and on this oxygen would be 0. But let's say, for the sake of example, that we have a very similar Lewis dot structure, but instead of having this lone pair in here, we erase it, and then we form another bond. So now nitrogen would have a formal charge of 0 and oxygen a formal charge of +1. Which one of these structures is the best? Well, the answer is this one. Why would that be? Well, the reason is because generally the Lewis dot structure that is best is the one where the negative charges are on the most electronegative atom. In this case, we do not have negative charges, but we have a positive charge. So the question should be, where should the positive charge be? In the most electronegative atom or in the least electronegative atom? Well, logic would tell us that the formal charge of +1 should be on the least electronegative atom, which in this case is nitrogen. So it is preferable to have a nitrogen with a +1 formal charge than an oxygen with a +1 formal charge, because oxygen is more electronegative, so it wants all the electrons to itself. So yeah, now that we have settled that, we can continue with the next Lewis dot structure. And by the way, if I'm making any mistakes, well, you can correct me in the comments. I'm still learning general chemistry, but you know, it's fun making these videos. Alright, so now we are going to do the Lewis dot structure of NO. Of course, of NO. Nitrogen oxide, I think. Anyway, we have the N. Let me make this white. Now we have N and we have the O. So they have a bond. And what should be the total amount of electrons in here? Well, it should be 5 plus 6, so 11. Now we should complete the octet, so let's try what we did before. Form 2 bonds in here. 1, 2, 3, 4, 6, 5, 6. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, and we can put one here. But if we do that, the formal charge of the nitrogen would be +2, and that's no good. So instead we erase these 2 electrons and we transfer them in here to form another bond. Now the formal charge of the nitrogen would be +1, which is much more manageable, and the formal charge of the oxygen would be -1, which is also manageable, and also oxygen is more electronegative, so it makes sense. And if we have +1 and -1, it gives us 0, so the molecule in its entirety is neutral. So this is consistent. So this is the plausible Lewis dot structure for NO. Well, that is what I would have said if there wasn't another alternative that had better formal charges. That alternative is the, let's say, correct Lewis dot structure, in which we have a double bond in here, 2 lone pairs on the oxygen, and we have another lone pair on the nitrogen. So here the formal charges of nitrogen on nitrogen is 0 and on oxygen is 0. So this is a better Lewis dot structure. And now we go for H2SO4, so sulfuric acid. We have, of course, the sulfur in the center. Then we got an oxygen in here, oxygen in here, oxygen in here, and oxygen in here. And now you might ask yourself, where do the hydrogen go? Do they go bonded to the sulfur or to the oxygens? Well, the answer we can get to by first doing the Lewis dot structure of just SO4 2 minus. So let's forget about the hydrogens for a second. If we have this, well, then we have a single bond going from sulfur to every oxygen. And how many electrons should this have? Well, it should have 6 times 5, so 30 electrons in total, because oxygen and sulfur are in the same group and they have the same number of valence electrons. All right, so now we need to do the octet rule. First, we can see that sulfur has a formal charge with just one bond to every oxygen of +2. And sulfur is on the period 3 of the periodic table, so it can have an expanded octet. So it can actually form another two bonds, here and here. We are not really going to talk about resonance structures yet, but it's good to keep in mind. All right, so now we need to complete the octet for the oxygens. We make that by putting lone pairs. So 3 lone pairs in here, 2 lone pairs in here, 3 lone pairs in here, and 2 lone pairs in here. And what do we got? We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32 electrons. Am I dumb? Oh, not really. It's because SO4 has actually 32 electrons. It had 32 electrons all this time. Why? Because it is an anion, so it has those extra 2 electrons. So the total is 32. All right. So we put this in here, and it's 2 minus, or minus 2. All right. So now let's say that having this, we want to add hydrogens. Could we really add hydrogens to the sulfur? If we did, well, we would have hydrogen over here and hydrogen over here. And then the sulfur would have a formal charge of 6 minus 8, so minus 2. And that is really unlikely. So most surely the hydrogens do not go in the sulfur. Instead, they are more likely to go on the oxygens that have just one bond. Why not on the oxygens that have two bonds? Well, because if we erase this lone pair and we made this, well, what would be the formal charge of this oxygen? It would go from being 0 to +1, and we also don't really like that if we can just do it like here. Oh, sorry for the interruption. My dear grandma just brought me food, which is great because I love eating. Anyway, so as I was saying, we do not really want the hydrogen to make a bond over here, but we could actually have the hydrogen make a bond with the oxygens that just have one. So let's take this, copy it, make this one smaller. And here. All right, so we get rid of the 2 minus because we are gonna have 2 hydrogens. And now, what would be the total number of valence of electrons in this? Well, it should be 32 also, because of the 1 valence electrons that each hydrogen has. But we add them in the following way. And like so. we add the hydrogen to the oxygens that already had just one bond. And how many electrons do we have now? Well, we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Am I dumb again? Well, maybe I don't really know how to count. Nah, I'm just messing with you. Anyway, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32 electrons, as we should. Alright, so now we're gonna skip right to the 11th question. Assign the formal charge to every atom. So this oxygen right here has a formal charge of +1. These carbons have 0. Why? Because oxygen has 6 valence electrons, and here we have. We have 1, 2. We divide this like this. Divide this. Divide this. 3, 4, 5. So 6 minus 5 is equal to +1. And we apply the same logic to every other atom. So all of these carbon atoms have a formal charge of 0. This nitrogen has +1 because it is 5 minus 4. And this carbon has a formal charge of -1 because it is 4 minus 5. It's -1. This nitrogen has a formal charge of +1. This B atom, this bor borium, I don't know how to say boro in English. This B atom has a formal charge of -1 because normally B has 3 valence electrons. Here it has 4 bonds. So yeah. Now we go, and the next are 3 plausible structures for the NCS minus ion. I don't really know how to say tiocyanato in English. Anyway, determine the formal charges. Which structure is the most important? Explain why. Alright, so what is the formal charge for this nitrogen? Well, it's 5 minus 2, 4, 6, 7. It's -7 minus 2. For this carbon is 0, for this other carbon is 0, for this other carbon is also 0. For this sulfur is 6 minus 5, so +1. For this nitrogen is 5 minus 6, so -1. And for this sulfur, 6, yeah. For this sulfur is 6 minus 6, so 0. For this nitrogen is 0. And for this sulfur is -1, so 6 minus 7. So why is the structure in the middle the correct one? Well, because the negative charge or the negative formal charge is supposed to be on the most electronegative atom, and in this case nitrogen has a greater electronegativity than sulfur. So if there is going to be a negative formal charge, it needs to be in nitrogen. All right, what else do we got here? Define resonance and structure and resonance structure. Explain the concept of resonance to explain why the 6 bonds in benzene have the same length. What is resonance? Well, resonance is a concept that applies when just one Lewis dot structure doesn't doesn't accommodate completely to the reality of a molecule. So, for example, in ozone, so O3, if you draw the Lewis dot structure of ozone, then you would say that this should be it. Yeah, with but so we have 2 double bonds on one side and 1 single bond on the other, but in reality these lengths here and here are the same, But if we just go by the Lewis dot structure, the length of the double bond should be shorter than the length of the single bond, because the double bond attracts more, let's say it that way. So in reality, the real form of ozone is kind of a mix between the two plausible Lewis dot structures. So yeah, there weird. There is this resonance in here that means that there are multiple Lewis dot structures, and a resonance structure is basically a Lewis dot structure that represents part or represents a molecule but not fully by itself. So why does benzene have the same length in each one of its bonds? Well, because the true form of benzene is an hybrid, a resonance hybrid, or of its two plausible Lewis dot structures, which have the double bonds in different places. So yeah, that would be the general explanation. Another thing to add is that in the real structure of benzene, there is electron delocalization. So for example, here in ozone, we know, okay, there are 4 electrons here, there should be 2 electrons here, but in reality, we don't have a double bond and a single bond to point to. We just have this sigma bond and this delocalized pi bond. So we do not know exactly where the pi bond is. The same happens in benzene. Alright, so I'm gonna skip past these resonance structures because there are a lot to do and we still have a lot of questions, so you can do them yourself. Alright, represent the Lewis dot structure, and then it asks us, SO3 2 minus, does it follow the octet rule? Well, in reality, it does not. So, where was I? Oh yeah, SO3 2 minus does not follow the octet rule because sulfur is in the third period, so it can have an expanded octet, and in this case it actually does. The central sulfur, if you do the Lewis dot structure, has a double bond, a single bond, and a single bond, and then it has a lone pair with it, which totals to 10 electrons, which is more than 8, so it breaks the octet rule. The opposite happens with BF3. We have here B, and then F, and then F, and then F, and it forms a bond in here. I'm gonna skip the electrons, you already know they are there, but yeah, B just has 3 valence electrons, so it cannot really follow the octet rule. So yeah, it doesn't apply to neither of these. Now, explain or at least tell if the next molecules are polar or non-polar. I put the polar in blue and non-polar in pink. So water is obviously polar. There is a great difference of electronegativity in oxygen and hydrogen, so there are partial charges. Oxygen has a partial charge negative, and hydrogen is partially positively charged. In SO2 there is also polar, because oxygen has a electronegativity of around 3.5, sulfur has an electronegativity of around 2.5. So yeah, the difference is big enough so as to make the molecule have a be polar. Alright, so here we will need a little bit of molecular geometry to explain this. And so water is polar, firstly, because the difference of electronegativity. But as you might have noticed, CO2 is non-polar, meanwhile SO2 is polar. Why is that? Well, the thing has to do with molecular geometry, because the difference of electronegativity from oxygen to carbon is also quite considerable. So what happens is the following. If we draw the Lewis dot structure of SO2, we have the S, we have the O, we have the O, yeah? And then we have these bonds, these double bonds, if I don't remember correctly. But if I don't remember incorrectly, but the important thing is that sulfur here has a lone pair. So, since it has a lone pair, that means like this, that means that it has a angular or bent molecular geometry. All right. Meanwhile, CO2, here we have the C, we have the O, and we have the O. It also has the two double bonds, but since the carbon does not have the lone pair in here, this has a linear molecular geometry. That means that the negative charges, I think it's done like this. Let's say it was like this, just for the sake of the argument, that the negative charges cancel each other out. So the partial charges cancel each other out, so there is not polarity in this bond, in these bonds. But meanwhile here, well, the charges are not organized linearly, so they actually apply. So the bonds are polar. Another more technical explanation is the dipole cancellation, let's say, that because CO2 has a linear geometry and it's symmetrical, and the dipole moments cancel each other out. So dipole moments, I understand them as kind of arrows that point to where the greatest electron density is. So in this case, you can see that there are two arrows pointing in opposite directions, so they cancel each other out. Meanwhile, here we've got these arrows pointing both down, kinda down, so they do not completely disrupt each other. So that's another explanation, more technical, as to why SO2 is polar and CO2 is not. All right. Now we go to SF6. Technically, there is enough difference between sulfur and fluorine to make the molecule polar, but again, because of molecular geometry, and the molecule just the dipoles cancel each other out, so SF6 is not polar. The same happens with CCl4, and the same with BCl2, which is also linear as CO2. Okay. And why is this? Well, because in, for example, SF6, there is F up, F down, F front, left, right, and center. And all of the moment dipoles cancel each other out, so really the molecule is not polar. Kind By the way, you might argue, well, CCl4 is not really symmetrical or doesn't look much like it. I mean, it's a tetrahedron that's that's kind of symmetrical, but does it mean that the charges, that the dipoles cancel themselves? Well, actually, yes, but in this case, there's another reason. And the reason is that all of the four atoms that surround the carbon are the same. But if we have something different, like HCCl3, the hydrogen atom disrupts the symmetry, so that molecule will actually be polar. Anyway, let's get going. So the angles of bond of A, B, and C are, well, we have first option 90-90-90. This is obviously not the case. If we have this N tan H H C, Well, this is obviously a lone pair, and this is obviously trigonal, pyramidal trigonal. Here, yeah, pyragonal. I'm gonna show you. Oh, let's see. Weird. Right here. So yeah, we got an atom with three other atoms and one lone pair. So that is a trigonal pyramid, and that has a bond angle of approximately 107, 109.5. So it's not 90 degrees. It might is and it's not 120. All right, then we go to C. Here we have this C double bond O, here C, and here a nitrogen. So this is trigonal planar. Let me change things up here. So this is trigonal planar, and that has a bond angle of 120. And finally, we got C. That is C, H, then C again, then C, and then H. That is a tetrahedron shape, and it has a bond angle of around 109.5 degrees. So the correct answer is C. Is E, I mean. Alright, now let's get to number 18. We are almost done. Oof, this has been, well, anyway. So the next compound has a certain Lewis structure, and it's the acetyl salicylic acid. I think that's how it is called in English, also known as aspirin. So we have a few places. We have place 1, place 2, and place 3. We need to specify what are the approximate values of the angles of the different bonds. What are the hybrid orbitals that are used around each central atoms for those bonds? How many sigma bonds are in here? Alright, so first question, in 1, well, we've got this carbon atom with the double bond, one bond, and another bond in here. That is trigonal planar, and it has a bond angle of 120 degrees. Then here we have another carbon atom with trigonal planar, so 120 degrees. And in the 3 we have an oxygen atom, so here that has two lone pairs and that has a single bond. This is pretty similar to the molecular geometry of water, which is angular spatial, or however you wanna call it, bent or V-shape also. So this is bent, which has an approximate angle of 109.5 degrees. In the case of water, by the way, is 104.5 specifically. All right, now next question. What are the hybrid orbitals of each of the central atoms? Well, this C atom has 3 electron domains, so that means that it is sp2 hybridized. Interesting. This should be sp2 hybridized. This other carbon atom has also 3 electron domains, so it's sp2 hybridized. This oxygen atoms has four electron domains, so it should be sp3 hybridized. So yeah, this oxygen right here has a sp3 hybridization, except it doesn't. Because there is a weird thing that I am still wrapping my head around, and is that when an atom is this like connected to a cycle, to a ring, it needs a pure p orbital to participate and help stabilize the ring. So because of that, this oxygen in actuality has an sp2 hybridization. Yeah, it's, for me, it's kind of funny. In reality, it's kind of weird, because you say, oh well, there are 4 electron domains in here, but in reality no, they are not sp3 hybridized, because the oxygen needs to give a pure p orbital for the ring, which is very weird. So let's keep going, we're almost done. Which one of the next molecules has a greater dipolar dipole moment? So here very quickly, dipole moment. Well, which of these atoms is more electronegative? Well, it's the bromine atoms. So the dipole moment should go this way. Of course, I might be wrong, but this is my understanding. So these two things cancel each other out because they have the same magnitude. They're going in opposite direction, so on and so forth. But meanwhile, these two here, um, the dipole moment, let's say, complement each other, or at least don't work destructively against one another, so B has a greater dipole moment. Something similar, well, something similar applies to NH3 and NF3. We have NH3, dun, dun, where the most electronegative atom is nitrogen, so every dipole moment points towards nitrogen, which makes it very constructive. Meanwhile, in NF3, the opposite things happen, because every F is more electronegative than N. The dipoles go in opposite directions, in different directions, and they exactly cancel each other. Well, and they work destructively against one another, or at least don't complement each other. So NF3 has a smaller dipole moment than NH3. All right. All right, once again. So the molecular geometry of this tin, I think SN stanyo is tin, and chlorine is, it's trigonal, pyramidal, trigonal, pyramidal. I don't know. Well, anyway, we will need to draw the Lewis structure for it. So SN, if I don't remember incorrectly, it is a member of the fourth group, so it has 4 valence electrons. So we have 4 plus 1 electron for the negative charge, plus 7 times 3. So we got 5 times 21, so 26. And then we had chlorine, chlorine, and chlorine. So 1, 1, and here. I would assume this is a double bond. Of course, well, we do not really need to concern ourselves with the exact Lewis structure. But okay, so let's do this, and let's complete the octet for this thing. Okay, so here we have how many? 6, 12, 18 electrons plus 2, 20, 22, 24, and there are 2 left. So we put those 2 electrons here on the SN atom, and now we have a lone pair. So we have a central atom, 3 atoms, and a lone pair. That is pyramidal, trigonal, pyramidal. I don't know how to say that in English, but anyways, it's not a tetrahedron because we have a lone pair. It's not planar because we have 4 things, and we have a lone pair. It's not a different T. Um, because for that we would need 4 electrons, if no 4 atoms and 1 electron, if I don't remember incorrectly. No, we would need 3 electrons, 3 atoms and 2 electrons, but it is not the case, and 2 lone pairs. And it is not oh, it's actually triangular pyramidal. Yep. All right. So yeah, let's keep moving. We are almost done. So what is the hybridization of the central atom of F4? Well, this is actually much easier than what we've done before. We have xenon, we have F here, F here, F here, F here. We have the bonds in here. And then we have 2 lone pairs, one over here and one down here. So that is 6 electron domains, and we have a hybridization of sp3d2 because that's the only one that has 6 electron domains. And as for the justification for this structure that I drew, is that we have a valence electrons from the xenon, we have 7 times 4 from the fluorine, so we have a total of 36. So we have 36 minus 8 because each single bond has 2 electrons. 36 minus 8 is 28. We complete the octet in every single fluorine, so 6, 12, 18, 24, 28 minus 24 is 4, so there are 4 electrons left. Sorry for the noise. Okay, so next question. How many sigma and pi bonds are there? Well, the pi bonds are easy to count. There is one pi bond for each double bond, and there are 2 pi bonds for each triple bond. So here we have 1 pi bond, 2 pi bonds, 3 pi bonds. Ugh. So not any single one of these answers is correct. So it's none of the before. But if we wanted to know the sigma bonds just for the sake of it, well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 sigma bonds. Now, we are shown the Lewis structure of carbon monoxide. What are the hybridizations of the atoms? Well, this is pretty easy. We've got carbon with 1 electron domain, 2 electron domains, so it's sp, and we've got oxygen with 1 electron domain, 2 electron domains, so it's sp for both. All right. Okay, we're almost done. And what are the hybridization of the following atoms, of the carbon atoms and nitrogen atoms? So we've once again got ourselves in quite the pickle because this is a ring, this is a cycle. So we need to keep in mind the rule that the conjugation rule. It doesn't exactly have a formal name, but the concept that for these atoms that are next to the ring, they need to have one pure p orbital so that they can stabilize the ring, participate in pi bonds, and whatever, so on. The point is that we need to take that into account. So let's start with this nitrogen. This has a hybridization of sp2. Why? Because it has 3 electron domains. So this one over here, double bond, this one over here, and the 2 electrons in here. The same thing applies to this nitrogen down here. It has 3 electron domains. So its hybridization is sp2. Well, you would think, oh, in actuality it is sp3 because and there is single bonds in here, and technically there should be a lone pair so as to make it 5 electrons, but no, because there needs to be a pure p orbital. So yeah, it's sp2. And with the carbons, where it's actually pretty easy, they all have double bonds, so it's sp2. And with this hydrogen, sorry for the noise, with this hydrogen, it has two bonds. It has one bond to a hydrogen and another hydrogen. I was saying this should technically have four electron domains, but because of the rule that I've already told you, it actually has just, well, it has an sp2 hybridization and a pure p orbital. So technically every single atom in here is sp2 hybridized. Again, I might be wrong, I'm still learning, but this is what I've learned so far. And now we are on the last three questions. I'm gonna skip this one because it's also about hybridization and such and such. So yeah, it's kinda repetitive if I don't remember incorrectly. What of the next substances has dispersion forces and dipole-dipole interactions? So first, dispersion forces or London forces are present in every single molecule, compound substance, because they are forces. I actually have a pretty neat slide on this. Let me show it to you. Give me a second. So we've got, man, this is so laggy. When weird. Oh, there it is. Okay, so this is hydrogen bonds. Where did I put it? Dipole-dipole interactions. Give me a second. Here it should be. Okay, nice. Oh, there is the slide. I don't exactly remember where I took this image from, but credit where credit is due. Oh wait, I think it. Anyway, so London dispersion forces occur when electrons randomly go to one side of a molecule, so they create an asymmetry and they create a difference in charge in the space. So this occurs pretty much at random, and it can happen in any substance. And when one molecule has a partial charge in one side and one partial charge in the other, that affects the electrons from the nearby molecules, making them move, creating a series of partial charges. So this force is pretty weak, is practically the weakest there is. But its strength depends on the size of the molecule, and if molecule has greater London forces, when the lead has a greater boiling point, you can see this phenomenon in the halogens. So yeah, let's keep going, we're almost done. Alright, so now that we have London forces out, let's talk about dipole-dipole interactions. They pretty much just happen in molecules with a great difference in electronegativity. Yeah, so we already know that CO2 is not polar, so that's out of the question. We also know that two of the same atoms don't really form not even polar bonds. The same applies with Br2, with B and Cl3. Well, here there is actually a difference in the electronegativity of chlorine and B, but dipole-dipole interactions are, let's say, more do not just occur because of the difference in electronegativity. So technically B and Cl have a difference in electronegativity that it's enough to cause polar bonds and should in principle be enough to cause partial charges. But in reality, BCl3 has trigonal planar geometry, so the moment dipoles cancel each other out. So yeah, unfortunately, BCl3 does not have dipole-dipole interactions. Meanwhile, HCl, well, it has a very noticeable moment dipole. So it does actually present dipole-dipole interactions. Oof. And we are almost in the last question. So number 27. I like that number. It's which of the next substances should exhibit hydrogen bridge bonds in a liquid state? All right, so hydrogen bonds just occur in molecules that have hydrogen, obviously, but that also have a that have atoms with very high electronegativities. So those atoms are, for example, H3. I'm joking. Nitrogen, oxygen. So for example, water, and fluorine. Yeah. So phosphorus doesn't count, H2 is not even polar, H2S does not count, CH4 is not even polar. So the only molecule that presents hydrogen bridges is NH3. So we finally did it. We finally finished the chemistry session. So I hope you liked it. I hope you learned something new. I hope it was useful for you. And who knows, maybe I will keep doing this kind of videos, but with with better quality in the future. So thank you for being here. Don't forget to like and subscribe if you have sat through all of my nonsensical ramblings at bits of chemistry. So yeah, thank you for being here and bye.